Hi, everybody, and welcome to Factor This. I'm your host, Angela Godwin. Joining me today, my guest is John Beckman. He is the Director of Business Operations, Fiber, and Access Solutions with Viavi Solutions. John, thank you so much for joining me.
Thank you, Angela. Appreciate the opportunity to be here with you today and speak.
Well, we appreciate having you. So let's dive in. Let's talk about how communication network testing contributes to reliability of the electric grid communication systems.
So grid operators use extensive communications networks for the control and monitoring of many elements of the electric grid, including transmission and distribution operations. Um, these networks can consist of fiber optic lines, microwave links, even wireless 5G and LTE links and other technologies. The critical thing is, or a combination of all those, but the critical thing is that these networks are mission critical to the safe and reliable operation of the electric grid itself. So therefore, just like anything that you have that you need reliability and safety out of, you need to test them. So testing of these communication networks is a critical element.
Yeah, that makes perfect sense. So what challenges do you think electric grid operators are facing without regular communication network testing?
Okay, so I think first and most obviously is if you're not testing the communication network, there's the potential for degradation and failure, which can lead to losing that visibility and control of key elements of the grid that's essential to the operator, right? But moreover, anytime you have a failure of that communication system, then you need to be able to diagnose, locate, and fix the problem too. And that can be labor intensive and time consuming, right? And when you think about operators, a transmission operator in Montana, for instance, that has a fiber optic link to a remote substation where a technician might have to drive an hour and a half in the snow to go fix a problem, you really need to be able to address that accurately and right the first time, in those conditions. Urban areas, present very different challenges, but equal in some cases in terms of getting access to the fault and fixing it. And finally, many electric operators utilize third-party providers for part of their fiber networks. And in case where you're leasing the fiber and there's a failure in the proximity to the leased portion of fiber, there can often be finger pointing issues between the operator and the fiber leaser that, you really, again, testing helps you resolve those issues quickly. So it's really key. And another point, this is kind of a long answer, they won't all be this long, but another point is when you're testing the telecommunication network supporting the grid, thinking about testing throughout the network life cycle is important. It's cliche to say, but testing when you're installing the communication link and activating it, getting it right the first time every time is really important because you just don't want to be running into problems that you could have solved. And a particular area when you're adding new grid communication elements is interoperability. Right, when new elements are being added into an existing grid, the possibility for different versions of hardware or firmware or protocol not being interoperable, and you really want to find that at the outset of the link. Also, post-installation periodic testing or monitoring enables operators to identify degradation or areas of poor performance but not outright failure, and gives them the opportunity to fix it before there's an outright failure. And then finally, as we talked about with kind of the three examples, like being able to having the tools and the knowledge to rapidly diagnose, locate, and fix problems, failures when they occur is essential as well.
Yeah, for sure. Now, what about like the overall reliability of resilience of the electric grid? How does network testing contribute to making that better?
Well, overall reliability is, I think, if you get a failure in the communications network addressing a portion of the grid that's essential to monitor or control, then you by de facto set yourself up for a reliability problem there. I think we'll get into a little bit of other reliability issues later in some of the questions with DFOS, but I think resiliency is a good question as for how communications, the communication network and keeping it up and running is really applicable to grid resiliency itself, and it's a lot of the same themes that you're hearing in a lot of the sessions here at this conference. First of all, vulnerability. Just like operators are assessing their grid for vulnerability to, wind damage and things of that nature, you need to be assessing by testing the communications for vulnerability. You might have areas of, a fiber optic line where the loss is acceptable for the communication required under normal conditions, but excessive for the length of fiber that you're testing over. That when it's subjected to heavy operational load or adverse conditions, would fail. You want to assess vulnerabilities like that before those vulnerabilities can be exploited or adverse conditions lead to failure. Secondly, I think, and it goes hand in hand with vulnerability, is kind of the inverse. You want to ensure robust performance of the network under normal operating conditions, like is my latency, throughput, bandwidth, signal to noise ratio, is everything within good metrics for normal operation of the network, so you have the confidence that it's going to perform when there's heavy operational communication load or some adverse conditions affecting the network, right? And that bleeds right over to the grid. Third, I think the interoperability, again, as we talked about, is a key thing, and the last time you want to encounter, there are some portions of the communication networks, emergency radio, emergency communication systems, that don't get used a lot until there's an emergency. That's really not the time you want to find out about problems with interoperability, right? So as we talked about, and then finally, from recovery standpoint, and in the recovery, you want to test the failover conditions of the communication. Some communication links will have failover or backup redundant links. You want to test that those are operating correctly. And there can be testing scenarios that actually invoke failure conditions to prove the failover, as well as to identify or to help you plan out in cases where there's not redundancy to what your recovery plan is going to be and better prepare. So all those four things contribute to resiliency, and testing is a key part of it.
That's great. And you brought up latency issues. How can communication network testing help to identify and head off some of those latency issues that you brought up?
So there are many critical links, communication network, that are tied directly to grid elements that have high reliability and low latency requirements. Teleprotection is one example of that, where the operators, depending on the teleprotection circuit, to trigger when there's an outage in one part of the grid to protect other parts of the grid that aren't affected by that outage, to keep it from rolling and negatively impacting the unimpacted portions of the grid. The circuit, the telecommunication circuit connecting those two teleprotection nodes has to be functioning with high reliability and low latency. Typically, fiber is the choice for those circuits because it is high speed, very low latency, and unlike metallic conductors, it's not susceptible to electromagnetic interference or corrosion and that, but fiber does have susceptibility. If the end faces of the fiber or connectors are damaged or dirty when they're connected to the equipment, it'll degrade the performance. Excessive bends in the fiber can degrade performance. All that really needs to be sorted out when the circuit is installed and activated. You want to prove the fiber is good, and then connect it to the end devices and verify the latency and interoperability again, end to end. So that's a key latency example.
So what about accurate timing and synchronization? How can network testing help verify that?
So we all know that timing and synchronization is critical to operation of the grid itself, right? You have to have good timing and synchronization to balance the generation with the load demand for the grid in general and prevent outages. Just like that, communication networks and many elements of the communication network require timing and synchronization to effectively pass error-free data from one point to another. So it's very critical to test the timing and synchronization of key elements of the grid itself, as well as the communication network supporting it. Additionally, there are a couple other benefits or important benefits of verifying timing and synchronization accuracy. You get more accurate time stamping for fault detection and logging, increased data integrity, enhanced monitoring and control functions in general, and then finally, when you're recovering from an outage, and bringing power back online, if you're not verifying the timing and synchronization of both the network and obviously the grid itself, then you're setting yourself up for bringing the power back online only to be degraded or disrupted by the timing problem. So,
right, that makes sense.
Key.
Yeah, perfect. So what about the integration of renewable energy sources into the grid? How can network testing support that?
Okay, probably hitting some of the same themes, but just like any other critical node in the grid, whether it's a substation or whatnot, renewable energy sources need to be networked with the rest of the grid from a communication standpoint for the same control and monitoring applications. For renewables, it's almost more important because of the variable nature of wind and solar, not always on, and we don't have control over the wind or the cloud, or so it's super important to have those elements, the renewable generation facilities networked to the grid, and additionally, I think when we talk, generally solar and wind are newer additions to our generation resources on the grid and come with newer equipment that has to be interfaced and linked with communication networks with older equipment. So common theme, verifying that interoperability when you're initially building the communication links to the renewable source is critical.
Excellent, excellent. All right, let's talk about distributed fiber optic sensing, or DFOS, as I understand it. How does that work?
So now we're shifting from communications test to using fiber. Fiber can be used to obviously transmit communications, as we've just discussed, but it can also be used as a sensor. And distributed fiber optic sensing uses a laser, just like communications, to send a pulse of light down the fiber. But instead of sending data end to end, we're looking at the backscatter from that light reflected back to the source and using different algorithms or technologies to analyze that backscatter in order to make accurate measurements of temperature, strain, and vibration or acoustic signature down the entire length of the fiber. So this enables operators to use the fiber not only as a telecommunications conduit, but also as a very accurate sensor that doesn't require power except at the endpoints and can be very accurate across those three technologies.
That's great.
Additionally, with machine learning and artificial intelligence, that vibration sensing, we've actually been able to identify discrete sources for the vibration. So it's gotten very sophisticated, and it can tell if that vibration is somebody manually digging or digging with an excavator. And in cases of subsea export cables for electric power, you can detect anchoring or fishing activities in the immediate vicinity of the cable as well, and identify them for what they are. So it's very exciting technology.
That is exciting. I imagine that has a lot of impact on the overall reliability and efficiency of the system.
Yep, absolutely.
Right. So let's talk about how DFOS can be employed in grid applications for increased damage prevention and rapid recovery, and tailing on to what you were just describing.
Yeah, so damage prevention is a key hot button for a lot of utilities, not just electric power, but telecom, gas, water. It's billions of dollars a year in expenses that in many cases are preventable if people, for example, would just call 811 before they dig, right? So distributed fiber optic sensing, where it's co-located with, say, buried cable, that acoustic sensing, distributed acoustic sensing I was talking about, can actively identify digging in the vicinity of a buried facility, whether it's power cable or subsea cable like we talked about, fishing or anchoring activity. But in the case of terrestrial buried power cable, if that information is then linked to an 811 call center, you can determine if that activity that's going on in real time was actually something that was permitted and filed with the call center ahead of time, and if so, is it occurring within the perimeter of the area that was permitted for it to go on. And this additional marrying of that information with the call center capabilities provides operators, and actually operators, the contractors or builders that are doing the digging, and the call centers with just a more powerful tool for damage prevention overall.
Yeah.
So that's one great example of the technology.
That's fantastic. That's great. What about physical security applications? How are those supported by fiber optic sensing?
So the same distributed acoustic sensing technology can be used for if the fiber is located in the immediate vicinity of a critical grid asset, for example, a substation, it can be used to detect potential tampering or intrusion of that facility. So not only damage prevention, but also physical perimeter security is another application of fiber sensing.
Excellent. So John, tell me, how can distributed fiber optic sensing technology improve electric transmission reliability and efficiency?
So as we talked about, distributed fiber optic sensing can be used as a very accurate linear sensor along the entire length of a fiber optic cable. And where those cables are embedded or co-located in close proximity to a power transmission cable, they can be used to measure temperature. Dynamic line rating here is a topic that has been of conversation in many of the sessions at the show. So dynamic line rating technology is an algorithm or model that takes various inputs to calculate the peak power at which an operator can operate an electric transmission line without exceeding limits and causing damage to the cable or impeding or degrading its long-term life. And distributed temperature sensing enables the operator to make very precise measurements of temperature along the length of the cable and feed into that dynamic line rating algorithm. And unlike point sensors that are placed at various points along the power cable to measure temperature, the distributed temperature sensing gives you a continuous temperature measurement along the entire length of the cable without the need to power individual sensors or network them back to either of the endpoints. So distributed temperature sensing is very much an enabling technology going forward for improving dynamic line ratings, accuracy, and thereby improving efficiency and reliability of the grid as a whole.
John, thank you so much for joining us today. Really appreciated the discussion and your insights. Is there anything else you'd like to share with our viewers, maybe somewhere they could learn more information?
Angela, thank you so much for having me. It's been a pleasure talking with you, and happy to share this information about network testing, telecommunication network testing for grid applications, as well as distributed fiber optic sensing technologies. And if your viewers want to learn more, they can visit viavisolutions.com and read all about it.
Perfect. Excellent. John Beckman, thank you very much for joining us today.
Thank you.
And thanks to all of you for tuning in. This has been Factor This. I'm your host, Angela Godman.